In this video, I'm going to do two more examples of derivatives that involve both log and exponential functions and may also involve the product rule. So here we have y equals the natural log of 3 theta times e to the negative theta. So we have the derivative of a natural log, right? We know how to do the derivative of a natural log. We're going to use the chain rule, which is the derivative of the argument over the argument. And then when we start looking at that argument, we have a product rule. And also because this exponent here has more than just one variable, like positive x, it's negative theta, we're going to have to use the chain rule. All right, so the derivative of y with respect to theta. So remembering what we have learned previously, dx of the natural log of some function of x, that would be g prime of x over g of x. If we're dealing with the natural log base e, and that's how we would set this up. So here I'm going to have d theta of 3 theta times e to the negative theta over 3 theta e to the negative theta. All right, so I've applied my derivative of a natural log. So now I need to find the derivative of my original argument, which involves the product rule. So if we had a first and a last, or an a and a z, the derivative of a product would be a z prime, first derivative of the last, plus last derivative of the first, z a prime. So I'm going to zone in just on this, 3 theta times e to the negative theta. And I might do that down here as some scratch work. So d theta of 3 theta times e to the negative theta. So first, 3 theta times the derivative of the last, e to the negative theta, then times the derivative of the inside, so that would be times -1, plus the last, e to the negative theta, times the derivative of the first, and the derivative of 3 theta is 3. So this is -3 theta e to the negative theta plus 3 e to the negative theta. So if I look at simplifying that expression we originally had, that would now be dy d theta equals, in the numerator I have -3 theta e to the negative theta plus 3 e to the negative theta, all divided by 3 theta e to the negative theta. Now, what most of us should notice at this point is that all of my terms, I have 3 terms, a first, a second, and then a third in the denominator, they all have an e to the negative theta. So those are going to reduce out, factor a GCF, and you'll cancel 1 over 1. And this leaves me with dy d theta is -3 theta plus 3 over 3 theta. You'll also notice that all of my terms now have a 3. That's the same as -theta plus 1 over theta. And, dy d theta, I would maybe just organize that and say 1 minus theta over theta. This is perfectly acceptable as an answer. Or you could say dy d theta is 1 over theta minus 1. Both of those mean the exact same thing. At this point, I would like to take a moment and look at that problem and work it out a little bit differently. If we look at differentiating this logarithm problem And instead of jumping straight into the derivative, if we look at using properties of log or algebra skills to simplify this first, it becomes a lot shorter. So one thing that we know is that if we have the log of a product, then that can be written as the sum of the log of each of those factors in the arguments. That's the natural log of 3 plus the natural log of theta plus the natural log of e to the negative theta. So now these are 3 really basic logarithms that we could take the derivative of. In this situation, the derivative of y with respect to theta. Looking at natural log of 3, that is a number or a constant, and the derivative of a constant is 0. Natural log of theta, that's going to become 1 over theta by our property for differentiating natural logs. And then this third one, we would need to use the chain rule there. But remember, the chain rule is the derivative of the argument over the argument. So that would be d theta of e to the negative theta over e to the negative theta. Simplifying this, dy d theta equals 1 over theta plus the derivative of e to the negative theta. We did that in the first part of this problem, but it would be negative e to the negative theta over e to the negative theta. Those would cancel, and we could rewrite this as dy d theta is 1 over theta minus 1. And if you think about going back to the previous slide, which I'll do right here, you'll notice that is the exact same answer, much shorter. So again, we always want to look at a problem and try to simplify it first using algebra skills. But it's okay if you don't see it. You can still get the answer. You might have to just work a little bit harder. All right, let's look at one more. In this example, we're going to differentiate the natural log of 2 times e to the negative t times sine of t. And for this example, I'm going to jump straight into my algebra rules for dealing with natural logs. So I can rewrite my function as the natural log of 2 plus the natural log of e to the negative t plus the natural log of sine of t. So I need to use parentheses there. Now, thinking about algebra, when the argument and the base, natural log is base e, match, we can cancel them, and that would just become the variable in the exponent. So that would become minus t plus the natural log of sine t. So now if I look at the derivative of y with respect to t, the derivative of a constant is 0. I don't need to write that. The derivative of negative t would be negative 1. And lastly, the derivative of a natural log chain rule is derivative of the argument over the argument. So that would be plus d dt of sine t divided by sine t. The derivative of sine is cosine. So dy dt is negative 1 plus cosine of t over the sine of t. And just for the sake of cleaning that up a little bit, we could write that as negative 1 plus cotangent of t. Final answer. So I hope that helps you a little bit more with taking derivatives of natural logs.